So I'm Jamie Wheat, and it is my pleasure to be here to deliver this talk on the updates relating to the structural simulations up to the 24x GA release. So there'll be three main sections to this talk, covering the updates relating to the 3D Experience platform, the Abacus solvers, and then some CAE updates. And hopefully, there will be time at the end for a few questions, and I'll do my most to be able to answer them. So there is a lot to get through, so it is going to come at a relatively fast pace. So just to cover off a little housekeeping, this talk covers information and updates relating to up to the 24x GA release. And for clarity, the release dates of the software shown on the slide. Obviously, this talk doesn't cover any topics around SIMPAC, CST, Wave 6 or PowerFlow, but I've included the dates just for your information. So if we start with updates relating to 3D Experience platform, and I guess just before I dive in, it's worth pointing out that this isn't all the updates and enhancements, it's just a selection of them. So there's plenty more that's in the release, and that's true for 3D Experience, the solver, and for CAE. So if we start with mid-surfacing, and this is an area of continuous improvement, specifically relating to cast components and plastic mold parts. And we're looking at improving the mid-surface extraction success, as well as the geometric quality. An example of some of the automation updates, there's a new option to create the non-manifold results for a mid-surface. Previously, you had to create those additional features manually. So now we have that automated option to do that. Also looking at the missing area visualization on the mid-surface creation. This is now shown on the mid-surface itself, as illustrated in the image on the lower left. So the solid is hidden, and it gives you an easier way to look at those errors. Looking at some of the automated FEM enhancements, defeaturing options, they've been exposed in the quad and the TechMesh user interfaces. So the parameters there are open rather than it just being a checkbox for things like fillet radii and hole diameters. So you get more details about those defeaturing options at the meshing stage. The thickness from mid-surface when creating shell sections, this wasn't available before. So now when you mesh that mid-surface, you can use the thickness data and the offset data that's held within that feature within the shell section creation. Partition hex meshing, there's a simplified workflow to include optional defeaturing to streamline the whole process, going from partitioning, creating the mesh, and then creating the solid property. Some other enhancements to mention, the assembly of mesh reporting. When a certain part of geometry fails to mesh, it's now easier to zoom in and find that part that's causing the issue. The preferred procedures for meshing, these have been unified and reduced by a factor of 2. And visible geometry selection now only selects what's visible and shown on the screen. Moving on to some meshing enhancements. So there's 2 new algorithms in the auto technique for quad dominant meshes, and these are shown on the right-hand image. If either of these are better than the standard mesh technique, then that's what's get used for the mesh generation. And by better, we're looking at both element quality and also mesh flow. For penetration fixing, so for digital penetrations, there's some initial manual tools to help identify and fix the penetrations within the model, specifically within the Mesh Edit app. And just to expand a little bit more on interference checks, there's an ongoing enhancement or a set of enhancements. And if we look at the zone manager, there's some associated functionality for quick identification and fixing of those interferences. Things like filtering on mesh name, creating groups for the nodes that are causing the interference from the context menu. There's direct access to the Edit Mesh app, whilst maintaining the interference check UI, and they're all aimed at simplifying that workflow to fix those digital penetrations. Other enhancements, we've exposed the curvature ratio in virtual topology. Previously, it was set to 0.1. It's now selectable from 0 to 1, so from never constrain edges to always constrain edges. Swept mesh volumes, we've added some functionality to edit the source mesh in the Mesh Edit app. So this is useful if you want a quad-only mesh for the source. The contributing FEM tree, functionality. This is now hierarchical, so it's much easier to see which FEM is associated to which contributing FEM. Interference checks on multiple instances of the same part now works as you would expect, and the quality analysis for assembly of meshes has been improved. Some modeling enhancements of note. So firstly, the cohesive property addition. So all the behavior for classical cohesive properties is now available in the UI for cohesive elements. Additionally, we have the definition of beam shear center for general beam sections, as well as beam offset for non-general beam sections relating to the 1 and 2 axis. And quite an important development, we now support the rebar layers and embedded elements. This was included to support the tire workflow, which I'll touch on a little bit later. And as you can see, rebar layers are defined at the section level. Continue with modeling. So we have multi-physics behaviors for couplings and ties, enabling you to couple more degrees of freedom, specifically looking at battery analyses. And from a virtual bolts point of view, you now have the ability to detect and select non-cylindrical holes for virtual bolts. So you can have combinations of a cylindrical hole at the top and a slot at the bottom, as you can see on the animation on the slide. And finally, for modeling, we now support rule-based connections for assembly of mesh configurations. This was previously limited to mesh of assemblies. And additionally, there's now support for non-uniform thicknesses that can be used to define the fastener size, as you can see on the image in the center. In relation to point fasteners, we now support folded parts. So where the situation is there's a fold in a part and there's multiple point connections on the same part, that's now supported. Also of note, you can now create cohesive elements in surface fasteners and the line fastener tool. And that includes the creation of zero thickness elements, and with the tie constraints being created automatically. Additionally, some functionality now exists for virtual fasteners, which allows fast creation of distributing couplings to couple a combination of lines and faces. And we now have a duplication of connections from the connections manager using the context menu. Some scenario developments. So we have an unrestrained mode detection for all linear static procedures. So this was a significant cross-departmental effort, and the intention here is to provide the user with a lot more information on why simulations have failed. It's kind of split into two levels. So from a designer level point of view, we're treating those unrestrained modes as a modeling error, and the user will be able to visualize those modes, but they will have to resolve them in order for the simulation to run. And the assumption that we're making is the expert users, they'll have a much better understanding of what these unrestrained modes are, and in some cases they'll be intended behavior. Right now there's a limitation that the mode shape animations, they're not resolved into the global coordinate system, so they can look a bit funky, but that's just because they're not resolved. We've also added the ability to quickly edit features through an enhanced UI from the assistant. So you can now get a filtered feature manager view of specific areas of interest. And the example being shown here is connections. So by selecting the pencil, you get an extra tab in the feature manager, and it has those features filtered out. There's a large effort ongoing to standardize the user experience across brands. And an example of that is shown on the slide on the left. So the target is to improve the look and the feel of all commands in a consistent manner. And this is ongoing work, so you should expect some updates in the following releases. There's also now a user preference to control the default licensing options, and these are inherited in the simulation dialog. So the user can specify the license model and the default license to use within that model, and it supports both simulation tokens as well as the newer sim unit and credit model. And this allows the enforcement by default of the embedded licenses, and therefore improving the efficiency of the licenses that you have. Some more scenario improvements. There's the addition of history outputs for general contact, and this is requested in the normal way within the scenario app, and it opens up the history plots in the results app. And these can also be used in design studies, for example. Nonlinear penalty contact options is now available in the user interface, which can be really useful for tackling those tricky and complex contact problems. And for explicit, we've added the ability to specify the use of automatic overclosure resolution, as well as the inclusion of contact mask scaling for cases where you've got a model that has lots and lots of contact surfaces. With some solver enhancements, we can now include and exclude regions for general contact on a step-by-step basis. So this may be useful in stamping or forming analyses, for example. It's accessible by adding an exclusion in step 1 and then removing that exclusion downstream in another step to expose those surfaces into the contact domain. And you can see an animation of that being shown. Fully coupled thermal electrochemical structural simulations can now include pore pressure. And this can be used to evaluate electrochemistry performance of batteries in cases where the mechanical response is important and in cases where you might want to study swelling, for example. So I guess this is used when there is a strong coupling between the fields, and the idea is in a single step you can include all the relevant boundary conditions and loads, and then you can add those dedicated electrical loads using the dedicated Butler-Volmer features for loading. There's an addition of a text field in the output requests for quick adding of specific user-defined set of outputs. So this is great for users that want to specify a long list of variables without having to traverse the tree structure to find them. We've had a lot of requests to enable quasi-static procedures for coupled thermal structural simulations. And this is useful in situations where there's time-dependent material responses like creep or viscoelasticity. And so this has now been added. There's also now a follower load option that's been added for force and torques, as well as fluid pressure penetration, and the latter enables simulations of pressure of the fluid penetrating between two surfaces that are involved in contact using a DS low card. I guess that's useful in like seal applications for doors and closures and things like that. There's going to be a new scenario manager, and this will enable convenient navigation of features for review. It'll be really useful for multi-step simulations when lots of changes occur. Some other key functions that get enabled with this as well is the ability to replace a step with a step of a different type and the insertion of a step before step 1. Both of these were 2 popular enhancement requests. The scenario manager itself is going to allow you to dive into the details of the simulation on a step-by-step basis, to review what's included, and then digging down into the feature itself to review how that feature changes over the step lifecycle. We've also added an interface for advanced users to specify the general solution controls for Abacus standard simulations. So this enables modifications of the convergence parameters, the field equations and the time integration scheme, as well as an automated approach for the equivalent of analysis equals discontinuous. The full tire modeling simulation workflow is now supported on the platform, right the way through from axisymmetric models with twist through the symmetric model generation and then onto steady state transport. And by enabling this on the platform, we're delivering the full ModSim experience for tire engineering workflows, including footprint and steady state rolling simulations. I think this is something that will be continued to be developed in the upcoming releases. From a durability perspective, the table on the upper right shows the access to the durability features and what apps and roles open up with what functionality. This is the licensing situation from the 23x FD01 release. For Verity, previously there was a plus or minus 22 degree tolerance and only on ideal configurations for welds. So that this has been removed, and also the configuration limit. So there are lots more configurations possible. Some algorithms that have been added or updated include the prismatic hull, Dangvang, and the Fatimi-Saisi. And also you can now use the fatigue algorithm override functionality to change the algorithm of what's specified in the material property. If you change the material property, you'd have to rerun the structural simulation. So by using the override function, you don't have to rerun the simulation. Some other enhancements of note, we've enhanced the Brown-Miller cycle data extraction, mainly for precision reasons under highly non-proportional loading situations. Material orientations supported by FE-Safe, and this is required to be able to support FK and welds on shells. And we've made some improvements to the mathematical consistency of calculations relating to stresses in the data sets with respect to Verity simulations. There's some new capability when visualizing results from the cloud, and this drastically reduces the amount of data that gets transferred from a user's local machine from the remote cloud. That's especially true when you're interacting dynamically with results. So as you can see from the graph, on a like-for-like comparison of post-processing tasks, there's a significant improvement in the time taken for certain tasks, and the table in the bottom left shows how we're achieving that. So what we're doing is we're using the cloud to render the results and the visualization, and we're just using pixel streaming to drastically reduce the data transfer from the cloud to the local machine. So this is quite a new development for R&D, and they're specifically interested in any feedback specifically around any niche issues you might face, and they will try and eliminate those gaps in upcoming FD releases. There's some new functionality to allow sensors that they can be created from XY data, and that includes from expressions, paths, and field variables. And again, they can be used in design studies. And we also have a new interface for simulation diagnostics. So this is a tree-based diagnostics UI, and it provides a way to see the detailed information in situations when the solver can't find a converged solution. And you get all the usual details like highlighting the areas of the model. And also there's now an option to export multiple XY curves in a single hit and into a single comma separated value or Excel file, and therefore enabling a more efficient export of bulk data. There's a new interface for filtering and selecting plies for models with composites. So you can select a specific ply when creating contour plots or sensors, display groups and XY plots, for example, and you can filter by ply name, ply angle, or material name. And we also have a new option to be able to query results by manually specifying nodes and element IDs available via the select by label option, as you can see illustrated. The contour plot interface has been enhanced to be able to define a reference frame for the elimination of rigid body motion, which is really useful in something like a drop test simulation. And the idea is to specify a reference system that mirrors the moving coordinate system, and then you eliminate that rigid body translation. It's worth pointing out that that's available for both native results and imported results. An enhancement relating to substructures and specifically using a display mesh. So a display mesh can be specified in the substructure generation step, and then that associated mesh can be used to display a representation of the full part in the usage model, which removes the need to do a recovery for visualization of results from the substructure. So that's what I have to show from a 3D experience point of view. So just to reiterate, it's not everything and not all the enhancements and updates, it's just a selection. But if we move on to the solver now. And if we start with some material updates, so the Wallenius-Landau material model, which was introduced in 22x FD01, this has been improved from a setup point of view. And the material behavior can now be characterized with a tensile test and a biaxial tensile test rather than needing the compression test data. I guess tensile tests are much easier to perform and much more common. Cure simulations has had some major enhancements relating to the addition of the grind and cure kinetics model, as well as being able to leverage the mean field homogenization approach to enable cure simulations of composites. We've also added the ability to use the user-defined cure kinetics using the ucure user subroutine. And just a word on mean field modularization. This is something that we're going to continue to develop, specifically looking at general failure models for composites. Beam elements and explicit, they can now be used with hyperelastic material definition. So useful in scenarios where you're looking at maybe sports shoes, for example. And the animation that's been shown here has damage included, just to kind of show that it's a general material and you can use all the subcasts from star material. Finite strain shell elements and explicit. The kinematics have been improved to be much more in line with Abacus standard, and this new formulation ensures a greater accuracy with stress calculations of those shells. And if you look at the graphs on the lower right, which represent the stress results from a multi-step load, unload, bending simulation. On the left, you've got the improved results, and after the loading and unloading process, you can see the stresses return back to zero, and on the right-hand side, you can see that there's an offset. Non-isotropic viscoelasticity. This is an alternative approach from mean field modularization to model composite materials, and we support transversely isotropic behavior, so something like a typical for a UD, unidirectional composite, as well as orthotropic for, say, short fiber composites. Can be calibrated using experimental data along with an FE RVE element, and it's defined by using the Prony series to specify the relaxation parameters for different directions. We've introduced a new C3D10T element for coupled temperature displacement analyses and explicit. This element supports all types of thermal load, so radiation, convection, conduction, etc. And it has a better accuracy and performance to the previous available C3D10MT element. And the majority of the improved performance comes from the fact that the C3D10T element has a longer stable time increment over the previous MT element. Batteries, they've had a big focus since 2019, and this is an ongoing activity, and that's still the case in the last few releases. The element library for modeling battery electrochemistry has been enhanced to include tetrahedron, prism, and reduced integration hexahedral elements, and there's also some axisymmetric elements as well. These greatly enhance the ability to model complex geometry and allow more accurate stress computation in constrained structures subject to volumetric expansion and contraction. We also now have a star uniform sub-option for the star coupling keyword to be able to couple voltage and temperature, for example. In addition to that, we have support for solid electrolytes, and we can now support battery aging simulations. Additionally, there's some new functionality for step control, which can be really useful in battery simulations, and I'll talk about that a little bit later on in the presentation. It's worth noting that there's extensive support for the new battery simulation workflows on the 3D Experience platform. Thickening of shells during simulation, I guess it's uncommon, but it's possible. So the example being shown here on the right-hand side is boundary condition, keeping the bottom plate fixed with in-plane compression of the middle plate, causing it to thicken. And then there's vertical motion of that middle and top plate, as indicated by the vector plot. There's some limits on the thickening behavior that you may need to consider. They're really related to contact. So I guess please bear those in mind if you're seeing issues. The fold tracking algorithm that was introduced many years ago, mainly for modeling airbags. And it was there really to increase the robustness of the solver. This is now considered obsolete. It's slower and it is less robust than the updated default tracking algorithm. And you can see some example statistics on the graph on the slide. For a while, there's been a circular approximation of beam cross sections relating to contact. So this has been worked on over the last few releases to be able to include realistic representations. And we're doing that by means of a cage of surface elements or contact facets around the beam. Not only does this give a more realistic contact result, but it also improves the general surface results, enabling the visualization of how those results vary across the beam section in Abacus Standard, for example. And you can see an example on the slide here with the realistic representation with their Jenga-style blocks falling over. A couple of enhancements to the code relating to scenarios where a point mass is sliding over some shell surfaces, for example. So as the contact transitions at the concave corner, the point mass is in contact with two of the faces. And before the fix, the all PW output variable, which is the work done by the contact penalties, was positive after the transition. And this is indicative of artificial energy being introduced, which could cause non-physical behavior in some models. After the fix, the all PW output is negative, which is partly associated to energy being stored in the contact penalty springs and partly dissipative. Solid element submodels, they can now be driven with a global analysis using beam elements. And along with this functionality, there is also a simplified keyword interface, and that includes the specifying of the local cuts, and these being driven by distributed couplings. There's also been some robustness enhancements related to edge-to-edge contact, specifically looking at solution noise. So there was a rather specific issue, but in general, that you should see reduced noise in explicit solutions which have edge-to-edge contact. And an extreme case of this is illustrated in the images on the lower right, where the two images on the right of the group, they show the desired symmetric response regardless of domain decomposition. And you can see on the left something, a few issues occurred. Just to point out that this is in the 23x FD05 release. So for the 24x release cycle, it's going to be an FD01. It won't make GA. ALE adaptive meshing is now available adjacent to general contact. Previously, this was only allowed for contact pairs in Abacus Explicit. So the arbitrary Lagrangian Eulerian adaptive meshing, this helps to maintain a good mesh after large deformations. And for this type of analysis, you'll see a much better performance with general contact over contact pairs. And that's generally related to the domain decomposition restrictions with contact pairs. So just to make a point about contact in Abacus Explicit, really you should be using general contact as the default choice now. And there's many reasons, but general contact has better performance, it scales better in parallel, it's easier to set up, it's more robust, and it now covers all the use cases in Abacus Explicit. And moving forward, it's going to benefit from the latest feature developments. So from a contact point of view in Explicit, we really are only developing general contact. Beam-to-beam adhesive behavior is now available. It's limited to circular beams in Abacus Explicit. That limitation doesn't exist in Abacus Standard. And I guess this is just a nice point to reiterate that you don't need to specify lots of parameters to get cohesive behavior to work. The default, that will use the stiffness related to the contact penalty stiffness, and it'll have no damage. And it's a good start to be able to introduce cohesive behavior into your modeling. There's a new thread-based sparse direct solver. I think it's fair to say that the majority of jobs that use Abacus Standard will use the sparse direct solver. And purely just looking at it from a solver point of view, this new thread-based implementation is much more performant than the existing solution. The biggest improvements so far, they're coming from Lanchar solves and from steady-state dynamics problems. And it's very well suited to low floating point to degrees of freedom ratio problems. And I'll touch on that ratio in the upcoming slides. So this new thread-based solver, it handles complex arithmetic much more efficiently than the existing hybrid direct sparse solver, and that leads to substantial performance improvements when it's used with SSD direct procedures, and that's true for a broad variety of models. Right now, there's some important and key limitations. They're in the documentation, and they're also shown on this slide. This is going to be a key area for development and R&D in the future to try and remove those limits. It's also worth noting that right now at higher core counts, the old solver may be faster from an end-to-end point of view, and that's due to the fact that parts of the solution with this new solver that just haven't been addressed yet. And again, this is an area for development. So just to expand on performance a bit more, and specifically looking at HPCs. So the old Abacus standard default MPI rank per cluster node, it's not really optimal for modern machines with high CPU core counts. So we've introduced a new job layout engine, which is often referred to just as JLE. So the JLE will adjust the job layout depending on the model features and the underlying hardware. And this slide just provides some motivation for trying to automate that job layout. So as CPUs have become more complex, it's not just a matter of running with more and more cores to get performance. If we consider older CPUs with lower core counts, all the cores, they had equal access to the system memory, and you didn't really need any special considerations or to do anything special with that CPU architecture to get good performance by just adding more cores. But with new CPUs with very high core counts, we're seeing some SKUs up to 96 cores. Cores are grouped into NUMA domains, so non-uniform memory access. They have their own connection to some portion of the system memory. They'll have a local cache, and sometimes they'll have a shared cache. There's additional cost associated with a core in one NUMA domain accessing data in the memory of another NUMA domain, and therefore that gives you that non-uniform part of the memory access. So to get the most benefit from additional CPU cores in this context and with this architecture, it's important to structure the job in a way that minimizes the data access across NUMA domains. And this is what can be achieved by controlling the job layout. So you can do this manually, and I'm sure there's plenty of customers out there that do their own benchmarking and control the layout of how jobs are executed. But from a default configuration point of view, we really need to do something different to get a better performance. So the new JLE will kick in with when CPUs are greater than 32, and it will use best practice heuristics to determine the job layout based upon the model that's being run, but also the hardware that it's being executed on. And you can see some comparisons on the graph in the center, comparing execution times with JLE and without JLE. And just to make the point that it's not a guarantee that it will be the absolute optimum best layout possible, but it will be significantly better than the previous default. So to cover off a couple of options that are available for certain scenarios, which again could help improve performance. So firstly, if we look at the iterative solver, and there's some things to consider to determine if the job that you're running is a good candidate for the iterative solver. So jobs that tend to show the greater benefit are ones that are more densely packed and bulky models, such as powertrains, and less so for sparse shell-dominated models. So if you look for the floating point operations per iteration, and you divide that number by the degrees of freedom in your model, you're looking for a number that's greater than 10 to the 7. Those values, they're available in the message in the DAT file. So if it's that number is greater than 10 to the 7, it would be indicative that the model is a good candidate for the iterative solver. And this ratio, this is what I was referring to with the new thread-based solver, but obviously you was looking for a low ratio, so you'd be looking for a number that was below 10 to the 7. There's a couple of points just to raise about the iterative solver. So firstly, the presence of certain modeling features, for example, high aspect ratio elements, they can make it unstable. and so therefore it's unsuitable. There's good documentation on the things that you need to consider if you're having to review a model. And secondly, we've been continually developing the iterative solver over the last few releases to make it more usable for a broader array of models. For example, with improved preconditioners for models with Lagrange multipliers, there's an unsymmetric version of the iterative solver. So, maybe what didn't work for you a few releases ago may work now, and we'd encourage you to try the newer implementation. So if based upon the model size and the nature of the job, the iterative solver would be beneficial, but you have something in your model that prevents it from being used, the next best option you've got to consider is GPGPUs. So for GPGPUs with the sparse direct solver, as I've said, this is a really good fallback if for some reason the iterative solver is not feasible. And you can use the same sort of benchmarks, the FLOP to DOF ratio relationship and dense bulky models when looking for good candidates. A couple of other examples that really benefit from the hardware. So the lower right graph shows the modal SSD speedups when using GPGPUs, and you can see some really good performance gains by the addition of just a single GPU. And the lower left graph shows the speedup with steady-state dynamics direct. And one of the factors here is that with frequency domain analyses, you're solving a complex system of equations, and that's much more computationally expensive than solving the same model from a static analysis point of view, and that's why you see good performance from GPGPUs. In the more recent releases, the Lanczos workflows have been improved, and that also includes the new thread-based solver that I've mentioned. And if you're using a release that's in, that should just happen by default if it's available to you. But there's also been other speedups relating to accelerated convergence within Solve. So there's a new shifting strategy that allows more iterations using a new termination criteria, and this increases the number of converged eigenvalues within a single Lanczos run. There's been development within the residual mode calculations, and we have a new method for supporting residual modes using a user-defined residual node set. And this is computationally much more efficient than using the conventional perturbation step preceding the frequency step. Also, you can use the rigid modes directly from a Lanczos solve rather than an approximation of rigid body modes. The AMS eigensolver as a process has been enhanced over the last few releases, and some of those are shown on this slide. The updates and enhancements are ongoing, and we're trying to cover each stage of the AMS frequency extraction process, and that includes plenty of development work ongoing for AMS acceleration using modern GPGPU compute cards. Just some examples of what's mentioned on the slide. There's a new residual modes computation for distributed loads using star D load and star DS load. So I guess in examples where you've got modal steady-state dynamic analyses with a pipe model and a pressure inlet surface. And we're extending the AMS capability for solving very large eigenproblems, extracting many thousands of eigenmodes. For example, fully coupled structural acoustic analyses of electric vehicles, for example. If we look at some steady-state dynamics, so firstly from a modal solver point of view, as I've mentioned, you can leverage multiple GPUs and benefit significantly in reduced solve time over CPU-only solves. In addition, there's been some updates to the SMP layout and automatic execution settings with modal SSD solutions. And in best cases, we're seeing something like 2 times speed up over the previous versions on really high core count machines. Direct SSD has had some optimization for multi-frequency analyses in recent releases, as well as the ability to partition the frequency space. So based upon every frequency being independent, and when you have sufficient compute resource, the runtime of steady-state dynamic analyses with lots of frequencies can be reduced by splitting the frequency points into several partitions and executing analysis for each of those partitions independently. So the performance gain here can be achieved by running those analyses for the different partitions simultaneously. There's no need to change the input file. To use this technique, you just access it by using the SSD split and the SSD partition options on the command line. And then you can use the Abacus ODB combine utility to combine those ODBs back into a single ODB. And just a few words on random response. So this has seen some really good performance enhancements over the last few releases. Improvements in element result calculations, nodal result calculations, and we've seen double-digit speed-up multipliers, even triple-digit speed-up multipliers in some extreme cases. But it's certainly not uncommon to see a 20x speed-up in models. Some more enhancements relating to linear dynamics. So prior to Abacus 23 hotfix 2, the computed acoustic contribution factors, they were saved to the sim file, but they weren't written to the ODB. I believe there was a knowledge base article that discussed the process of how you can visualize those ACFs. But from 23 hotfix 2 onwards, you can save those computed contribution factors to the output database. So if you request history output, you'll get those computed ACFs as history curves, and obviously field output is only really relevant for grid ACFs. The normal velocity output has been updated to make it easy to access in the ODB, and this is important for external acoustics. Additionally, we've added local normal stiffness outputs, which is an approximation, but an accurate approximation, and it calculates the local normal stiffness of each point using superposition, rather than having to run many different simulations to determine the normal stiffness of each point. And therefore that's saving a significant amount of solve time. The joint sensitivities, they can be extracted for composite shells, as shown on the slide, and we're supporting design variables of ply angle, ply thickness, and you can access these by using a distribution table. There's plenty of options for design responses, displacements, forces, stresses, stiffness, etc. But these can also be combined with the user-defined element design response to obtain sensitivities for different composite failure measures such as SIWU and Hoffman. With this, you can run the model in SMP and DMP, and as you can see, we're supporting static and dynamic simulations, but jobs with eigenfrequency or steady-state direct, they're not supported, as well as inertial relief is not being supported. For steady-state dynamic direct problems, you can extract sensitivities for displacement, velocities, and accelerations. In this instance, distributed memory parallels not supported, and the sensitivities and design responses, they're aggregated over specific frequency ranges, which is specified by the user. Just to mention the substructure display elements again, but more from a solver point of view. As I mentioned, they're specified, they're defined at the generation level by selecting a specifically created display surface element or truss elements, and you give them a null material property. And the display feature is activated at the usage level in the substructure property. The display nodes and on the elements are then created automatically. And you can see an example of that on the slide now. For monitoring substructure nodes in the usage model, so the monitor nodes, they're created using a node set in the generation model, and then again they're applied in the substructure property in the usage model. The monitor nodes then not connected to the usage analysis mesh, so they don't affect the simulation results, and obviously that means that you can't apply loads or boundary conditions or anything like that. You can request history output on those nodes, and there's some predefined options which are shown on the slide. And also you can see the graph of a comparison of two analyses. So one showing a native FEM solution, and the other line showing a substructure, a use solution. I alluded to step control when I was talking about batteries earlier in the presentation, and this slide just shows some of the details of what can be achieved. So this has been a two-part development in 2023. So first, the implementation of star step control, and then followed by the refinement functionality to more accurately hit the target state. So based upon the value of a sensor and the criteria applied, it's possible to control the time increment, as well as the ability to end the step in the analysis and continue into the next step. So if you look at the upper right graph, you can see that step 1 was terminated on the sensor reaching a certain threshold value, and then continued in step 2. And building on that in the lower left, you can see that the time step size changes after a certain sensor value, and then again we're ending step 1 and starting step 2. And there's various options within the keyword. So you can refine the time step between two sensor values to really concentrate output. You can end the step, you can continue the step, and also you have the option to end the analysis upon the sensor value being reached. Some words about Abacus explicit enhancements over the past few releases. So from a CAL point of view, so coupled Eulerian Lagrangian, there's been significant performance updates with reference to scalability of the contact calculations and how the cost is shared within MPI ranks. And this is tracked and also illustrated with respect to the internal hydroplaning tile model as illustrated. And you can see a graph on the right-hand side showing a comparison for different job layouts for the 5-vehicle crash model, and there's a video above there showing more vehicles, but it's using the same framework. So you can see that there's some good improvements with using a hybrid approach with varying number of CPUs, and I've seen this model scale really well up into the thousands of cores. And there's plenty more really, but I think this just highlights some of the developments in explicit, specifically relating to performance, capacity, scaling, and quality. So I guess we're always looking to be able to solve bigger models faster by using better scaling strategies, as well as leveraging the newer CPU architecture. And overall, we continue really to prioritize accuracy and repeatability within explicit developments. Okay, so to finish up with some enhancements in the CE product. So there's an enhancement that allows you to copy sets, such as those coming from an instance model, for example. This is available in the assembly context in CE. Currently, it's only available via the model tree from a right-hand mouse menu. You can't access this via the menus or from the set manager. For linear perturbations, you can now specify the LCP contact for solution technique, as well as full Newton. So this is to access the small sliding frictionless contact model. We've added support in CE for creating channel and hat beam profiles. So these were added to the Abacus solver a few releases ago, but there's lots of parameters involved with setting up these sections. So, you know, of course, it's quite helpful to have these profiles supported in the interface. And you can also see the console plot of the hat section showing axial stress variation along the length of the beam. We've enhanced the support for star distributing to include rotational couplings. And you can see here that when you're defining the coupling constraint or discrete fasteners, you can specify the rotational coupling type as either continual or structural. There's a small enhancement relating to Tosca optimizations. So you can now request specific DSLS sim unit licensing types, tokens or credits in the optimization job, and CAE will pass this through to Tosca. Unfortunately, CAE doesn't actually know what is available to the optimization job. So from the UI point of view, it's always going to be shown like this. CAE also has added support for step-dependent general contact in Abacus Standard. I mean, this might seem like a small thing, but it was really quite a difficult development for CAE. And you can specify those contact inclusions and contact exclusions for general contact from one step to another. Other enhancements, we've made some improvements to the visualization of SPH particles in Abacus Viewer. Previously, the particles were shown as filled blobs, even in wireframe and shaded modes. So now you should see those particles as they're supposed to be seen. We've added support for requesting P-force, contact force, which is the nodal force vector for fluid pressure penetration loading. The support for star contact mass scaling for explicit, and you can specify the surfaces for the contact mass scaling. Prior to 24 CAE releases, there was already support for beam offset sections in the general beam section, but we've now added that for the star beam section as well. And from a scripting point of view, so the mass property query is quite a useful and powerful tool in the queries, and it was available in the API from a pre-processing point of view. But some scripting users felt left out because it wasn't available from a post-processing point of view. So we've now corrected that shortcoming in the 24 release. And just to finish, there's the upcoming update to Python 3 with the 24 release of Abacus. So this will have an effect on scripts and plugins. Please make use of the upgrade script plugin, which in most cases should make the necessary changes. But there's also a few other things that you might need to consider. So potential areas that could be impacted with the scripting change shown on this slide. I guess some are really obvious, like scripts, plugins, and custom applications. But you should be careful and consider things like the Abacus v6n file that's interpreted by Python, the star parameter keyword in the input file. Again, that's also interpreted by Python. So you may need to be careful about integer division calculations, for example, on the differences between the two Python versions. And for those that use the batch system scripts provided by DS, there's a knowledge base article that has updated Python 3 versions. And that is all I've got to say today.
Okay, thank you for your presentation, Jamie. We now have some time for the questions.
Okay, so are there any situations where we should be using contact pairs in explicit? I would say, kind of as I alluded to in the presentation, that there isn't a situation now where general contact isn't supported, and I think it should be the default choice for Abacus explicit moving forward. You'll get access to the developments. It's going to perform better. It should be easy to set up. It should be more robust. There should really be no reason that I know of to use contact pairs in Abacus explicit. What is the future of Abacus CAE? As far as I'm aware, Abacus CAE will continue to be supported. I mean, I think it's clear that we have the 3D Experience platform, and that's where we put a lot of development activity. But I think you can see from some of the updates here, there is still development ongoing into Abacus CAE, so it's not end of life yet. When using SSD split, how do the jobs get counted in terms of token usage? So as far as I'm aware, each of those independent solutions, they're just an independent job. So you can use, like, if you from a single solve point of view, let's say you're using 40 CPUs and you want to split it into 4, then you can just use 10 CPUs with them, all those 4. But obviously that will affect your token usage, but it is based upon the number of tokens that is being used for that partition. Next question, is JLE aware of high core count on non-multi-CPU platforms, specifically thinking about Threadrippers? I think so, yeah. I think as long as the Abacus is aware of the CPUs and the CPUs that you're using and the core count, then JLE should take that into account. That's all the questions that I've got. Is that right?
There's one additional one coming.
Can you elaborate on the sensor usage for step control? Can one use reaction forces, displacements, and connector forces? I don't know the answer of that off the top of my head. Vanessa, if you can take whoever asked that, and I can get back to them at some point.
Yeah, this question is posted in the Simulia community, so okay. We can just add the answer afterward to the post. Yep, so this was the last question for today. So thank you again. Thanks for joining today's Release Tech Talk. So we hope you enjoyed the session and you will also join our upcoming ones. And with that, have a nice rest of your day and goodbye.
Thanks, Vanessa.